Hello everyone and welcome back to the Regents Chemistry Review series. In this video, we are going to talk about solutions. So let's start with the very basic definition of solutions. The solutions are generally homogeneous mixtures, which means if you look at the any solution, everything in that mixture is completely dissolved and it appears the same everywhere. We can separate them using physical techniques, for example, distillation or crystallization. And what happens in this homogeneous mixture is that all of the particles that are in the solution, they are spread uniformly or evenly throughout the second substance. So remember that we can have the different types of solutions that we'll talk about in a little bit. So for now, let's focus on the example of dissolving sodium chloride in water. Remember that would make an aqueous solution because whenever we dissolve something in water, it makes an aqueous solution. So when sodium chloride goes in water, because it's an ionic compound, it's going to dissociate, meaning it's going to separate out into its ions. So the positively and negatively charged sodium and chloride ions are then attracted to the positive and negative ends, or more specifically, the partial positive and partial negative ends of the water molecule. They form what we call the molecule ion attractions, and that's how sodium chloride dissolves in water. So, the different type of solutions, as I mentioned, that we can have is we can either just have different solids mixed together and they make something that's called alloy. We can have different liquids mixed together, for example, coffee and milk. We can also have different gases mixed together. But besides that, we can also make a solution using a solid and a liquid, or liquid and a gas, stuff like that. So there are different possibilities for making the solutions. So let's familiarize ourselves with some of the very basic terminology for solution. So first of all, as we mentioned, solution is a homogeneous mixture that is made up of two or more substances that are physically combined. And then there are two important parts of a solution. We have a solute and a solvent. So the solute is the substance, for example, salt or sugar. So that's the substance that is being dissolved. And then your solvent is what we use to dissolve our solute in. So for example, in case of the aqueous solutions, water is going to be the solvent, and whatever we are dissolving in water is going to be our solute. So solubility then is how much of the solute can we dissolve in a given amount of solvent at a specific temperature. And remember that every substance out there has a different solubility. So we are given the solubilities of some substances in table G. We'll look at that table in a little more detail in a little bit. So then the two terms associated with solubility are soluble or insoluble. So if we are looking at a substance that dissolves completely in our solvent, then that thing is soluble. And if our substance cannot dissolve completely in the solvent, then it is insoluble. So that insoluble substance in our solution precipitates out. This normally happens as a result of a chemical reaction. So for example, we started with two things. When we combine them, one of the products that they form turns out to be insoluble in our solution. So that product is going to precipitate out of the solution. So we can predict if any compound that is going to be our reactant or product, if it's going to be soluble or insoluble, using table F that we will look at in a little bit more detail in a bit as well. So let's talk about solubility. If you're trying to determine the solubility of ionic compounds are normally soluble. Because most ionic compounds, when they go in water or just any solvent, they have the capability of dissociating into ions. And as you can see in this picture over here, we have sodium chloride in water. So the positive and negative ions of the sodium chloride are attracted to the partial positive and partial negative sides of the water molecule. So this is how most ionic compounds behave in solutions. However, there are some ionic compounds out there that are insoluble in water. So we can determine what those are using table F, which again we'll look at in more detail in a bit. But if you're talking about covalent compounds, there's a very general rule about covalent compounds and their solubility. And that rule is like dissolves like, meaning if your solvent is a polar covalent compound, then that solvent can only dissolve polar covalent solutes. If your solvent is non-polar covalent, then it can only dissolve non-polar covalent solvents. So we cannot dissolve non-polar in polar or polar in non-polar. So that's what like dissolves like means. So there are some factors that can impact the solubility of our solutions. The first is the surface area. So if the particles have more space available to interact with each other, then of course the solubility is going to be higher. They're going to dissolve faster in general. If we stir the solution, again we are giving more room for our particles to interact with each other, so the rate of dissolving is going to be faster. In terms of temperature, if we for solids and liquids, because the particles are somewhat closer together, so when we increase the temperature, that increases the speed of the particles. So remember, temperature is the average kinetic energy, so increasing the temperature is going to increase the speed of the particles, so that increases the solubility, because again now particles are interacting with each other more. In case of gases, however, if you increase the temperature, the solubility decreases. And the reason for that is because when gases have a lot of space between their particles. So when they start moving very fast, and let's say we have an open system, the they tend to leave the solution, because gases in general do not want to be with the liquids, because liquid particles are somewhat closer together. So when we are forcing a gas to dissolve in a liquid, we are forcing the gas particles to come closer together, which gas particles do not want. So if we increase the temperature, the particles are going to start moving faster, and whenever they get the chance, they are just going to evaporate out of the solution. So they're going to leave the solution. So for gases in general, if you increase the temperature, that is going to decrease the solubility. So think about the soda can example. If you leave your soda can open at room temperature, so on the kitchen counter, compared to if you leave the soda can open in the refrigerator. The one that's on the kitchen table is going to go flat faster compared to the one that's in the fridge. So lastly, let's talk about pressure. Pressure means if we are bringing the particles together. So in case of solids and liquids, pressure technically has no effect on solubility, because their particles are already so close to each other that no matter how much pressure we apply, that does not really make a huge difference to the space between the particles. So gases, however, because the particles are very, very far apart from each other, so when we increase the pressure of the gases, we can bring the particles together. So that can increase the solubility. So think about your soda can again. When the can is closed, there's a lot of pressure buildup in the can. So by increasing that pressure, we are forcing the gas to stay dissolved in the liquid. So let's talk about the concentrations of liquids, which basically there are two terms that you need to know for concentration. We say that a solution is concentrated if we have a lot of solute in dissolved in our solvent. However, if there's less amount of solute in dissolved in the given amount of solvent, then we say that the solution is dilute. So concentration is really how much of the solute do we have dissolved in our solution or in a given amount of solvent. So let's look at these two pictures over here as an example. So This one over here is your concentrated solution. So as you can see, concentrated solution has kind of equal amount of the solute and solvent particles. So there's a lot more, there's a lot of the blue particles, which is the solute, and there's also a lot of purple particles, which is the solvent. Compare that to the dilute solution. This is where we have a lot of the solvent, so a lot of the purple molecules, and very little of the blue particles, which represent the solute. So normally, if you take a concentrated solution, and this is what they're doing in this picture, if you take a small amount of a concentrated solution and you just add more solvent to that, which in most cases is just water. So if you add more water to your concentrated solution, you can make it dilute. Okay, so next up, we are going to talk about the three different types of solutions that we can have based on the concentrations. So depending on how much solute we have dissolved in the given amount of solvent, we can either have an unsaturated solution. So this is the type of solution that does not have the maximum amount dissolved, meaning we still have some more room to add more solute and will still be able to dissolve the added amount of solute. Saturated solution is the one that has reached the limit, so it has already dissolved the maximum amount of solute that we can possibly dissolve. And by the way, just a quick note here, because I forgot if I put this in my PowerPoint anywhere else, but remember that saturated solution is also called the solution equilibrium, because this is the point where the rate of dissolving is equal to the rate of crystallization, meaning the rate at which our solute is breaking down into ions is the same at which the ions are then coming back together to make the solid again. And then unsaturated solution is where we have more than maximum amount of solute dissolved in our solvent. So this normally happens when we increase the temperature, and by increasing the temperature we can kind of force more solute to dissolve in a given amount of solvent. However, what happens eventually is that if when the temperature goes back down, that extra amount of solute that was once dissolved in our solution can be crystallized. So if we kind of try to understand this concept a little bit more using table G. As you can see, table G gives us the solubility curves of different substances. So what the solubility curve means is that at a given temperature, how much solute do you need of any substance to make a saturated solution? So the lines that you see, and by the way, this is a temperature versus the solute per 100 grams of water graph. So please pay attention to the 100 grams of water, because remember that if the graph is telling me that at 0 degrees Celsius I need 90 grams of NH3 to make a saturated solution. Remember that this 90 grams is for 100 grams of water. So if I decrease the amount of water and make that like 50 grams of water, then I'm going to need 45 grams of NH3 to make a saturated solution. So the lines in this graph represent the saturated solution. So that is represented by number 1, I believe. If we are looking at any area underneath the line, so let's say by line I mean this part over here, any area underneath the line is going to be the unsaturated solution, because that means we do not have the maximum amount of solute dissolved yet, and any area that we might have above the line would represent the supersaturated solution. But then again, there are some tricks for the supersaturated solution that you must keep in mind, so we'll talk about that in a little bit. So for number 1, we have a problem to think about. So we are saying that at this point we have 45 grams of potassium chloride at 60 degrees Celsius and 100 grams of water. I am going to try to see if I can maybe change the color or something. No, I cannot. Oh, I can. But first of all, let me erase this thing that I just made. Okay, so if we are at 45 grams of KCl at 60 degrees Celsius. So here's 60 degrees Celsius. Here is your 45 grams. And we have this in 100 grams of water. So because this one is right on the line, that means we have a saturated solution. So as I mentioned earlier, saturated solution represents the solution equilibrium, which means this is the point where the rate of dissolving is equal to the rate of crystallization. So let's talk about the second part then. So if we have 30 grams of KCl at 50 degrees Celsius in 100 grams of water, so that will be this point over here. So at this location, because it's below the line for KCl, so that means we still have the unsaturated solution. By the way, the line for KCl is this one. So now that our point is below the line, we have an unsaturated solution. So that means there's more dissolving happening at this point compared to crystallization. So there may be very little to no crystallization at the moment. Um, and then if you look at third point, so right now let's say we have 60 grams of potassium chloride at 50 degrees Celsius in 100 grams of water. So now this point is above the line for KCl. So that means we are looking at a supersaturated solution. My apologies. This one should say supersaturated. So we are now looking at a supersaturated solution. So this is where there's more crystallization happening compared to dissolving. So as I mentioned earlier, in order for us to say that this is a supersaturated solution, whether you're given this in a question or a passage or whatever, it should specify somewhere that all of that solute that we are adding, all of the 60 grams that we added to this solution was once completely dissolved. Because in order for any solution to be classified as a supersaturated solution, our solute should dissolve first completely and then crystallize. So if the solute never dissolves, then it's just a supersaturated solution. So if you keep adding the 60 grams, because at 50 degrees Celsius, the amount that the maximum amount of KCl that we can dissolve is like about 42 grams. So after that 42 grams, if you keep adding more solute but it never dissolves, that means we just have a saturated solution. Okay, so moving on, let's look at how to use table F to determine the solubility of ionic compounds. So the way your table F is divided is that the first column gives you some ions that, if present in a compound, makes that compound soluble. However, there are a few exceptions to that rule. So for example, if you look at halides, normally if you find halide in any compound, the compound is going to be soluble unless your halide is combined with silver, lead, or mercury. Okay, and then in the next column, we have all of the ions that can make the compound insoluble unless we have any of these exceptions. So for example, if your compound contains carbonate, it is going to be insoluble unless your carbonate is combined with any of the group 1 ions or with ammonium. So if it is combined with either the group 1 ions or with ammonium, then that means it's going to be soluble. So let's look at some examples. So we have lithium hydroxide. So we can see from the table that lithium is a group 1 ion and there are no exceptions to that. It's always soluble. And then hydroxide is insoluble unless it's combined with group 1 ion. So because in this case lithium is combined with the group, hydroxide is combined with the group 1 ion, that tells us that it's going to be soluble. Here's another example. We have hydrogen perchlorate. So sorry, this was just chlorate. So for chlorate, our table says that it is soluble always, and there are no exceptions. And hydrogen is a group 1 ion, so those are also always soluble. So this one is going to be soluble. So when we say that something is soluble, that means when it goes in the solution, it can dissociate into ions. And because it can dissociate into ions, it's also going to be an electrolyte. So electrolyte means it can conduct electricity. So can conduct electricity. But if we say that something is insoluble, that means when it goes in the solution, it cannot dissociate into ions. So it's just going to precipitate out as a solid. So this one will not be able to conduct electricity. All right, so let's talk a little bit more about the concentrations of solutions. So concentration gives us the specific amount of solute that is dissolved in a solution. So there are two ways or two units that we are going that we learned to find concentration. There are definitely more than these two units out there, but we only need to know two of them. So the first one is molarity, the second is parts per million. The equations for both of them are given in table T. And they look like this. So molarity is the moles of your solute divided by the liters of solution. So in most cases, you might not be given the moles of the solute. Instead, you might be given the grams. So you can use this equation that we learned in one of the previous units to find the number of moles. So the number of moles is just going to be the given grams divided by the gram formula mass or the molar mass. So let's look at some examples over here. So we are given 5 grams of calcium chloride in 250 milliliters of a solution. What is the molarity? So there are two tricks here. First trick is that they gave us 5 grams instead of moles, so we're gonna have to convert those to moles. And then the second trick is that they gave us 250 milliliters of the solution instead of liters. So we're gonna have to convert that to liters as well. So let's go from 5 grams to moles. So to do that, I'm just gonna use the equation. So moles is equal to the given mass, which is 5 grams. And then for your gram formula mass of calcium chloride, calcium has a mass of 40. We're gonna add that to 2 chlorine. So 1 chlorine has a mass of 35.5. So when you do the math, it's going to add up to about 111 grams per mole. So the grams cancel out with the grams, and you get somewhere around, I believe, like 0.045 moles. Okay, and then let's do the milliliters to liters. So that is 250 milliliters. So to convert that to liters, we can just go ahead and divide this by 1,000, or you can do like the fancy dimensional analysis and say that we have 1,000 milliliters in 1 liter. So the milliliters cancel out with the milliliters. So that is going to be about 0.25 liters. Okay, so now that we have both of the numbers that we want to plug in the equation, let's just go ahead and plug them in the equation. So 0.045 moles of the solute over 0.25 liters of the solution. And that is going to give us the molarity, which is 0.18 molar. Right, let's look at a different example. So in this case, it's saying how many grams of sodium chloride would you need to make 100 milliliters of 0.5 molar solution. So they already gave you the molarity and they're asking for the grams. So because you're already given the molarity, that tells you that you have to use the molarity equation. But then remember, for the molarity equation, we only have 3 quantities in that equation. One of them is molarity, which is given. The second is the liters of solution, which we can calculate using this. So 100 milliliters is just going to be 0.1 liter because you divide 100 by 1,000. And then if we plug these two numbers in the equation, we can get the moles. So molarity equals moles over liters. To calculate the moles, we can just multiply the molarity and the liters. So that gives us 0.5 times 0.1, which is going to be 0. 0.05, I believe, moles. So now that you have that many moles, all that you need to do is go from moles to grams. So we can use this equation over here to calculate the number of moles. So if we have 0.05 moles, we can, given the given mass we don't know, that's what we are calculating, so we can set that equal to x. And then for the gram formula mass of sodium chloride, sodium has a mass of 23 and chlorine has the atomic mass of 35.5. So when you add both of them, you get like 58.5 grams per mole. So now moles are going to cancel with the moles, but also if you multiply these two things, x is going to be equal to about 2.925 grams of sodium chloride. So that's your answer. So let's look at the second unit of concentration, which is parts per million. So this is the unit that expresses the mass of the solute that we have dissolved in 1 million parts of a given solution. So think about this solution, and let's say we are looking at the million particles. So the ppm gives us the concentration of our solute, or the mass of our solute that we have in a millionth part of this solution. So maybe if we only focus on this one particle over there. Okay, so the equation for parts per million is also given in table T. So that's mass of solute over mass of solution times a million. Sometimes they might not give you the mass of the solution, and you might be given mass of solute and mass of solvent separately. So just remember that to calculate the mass of solution, you're just going to have to add both of them. And sometimes in the question, you might be given parts per million. So in that case, instead of multiplying with a million, you're going to have to divide by a million. So let's look at some examples. If a solution contains 0.75 grams of solute in 150 grams of solvent, calculate the concentration in parts per million. So here, as you can see, they gave you the mass of the solute and the solvent, but no mass of the solution. So when you are putting this in the equation of parts per million, you're going to write 0.75 grams of solute at the top, and then for the bottom, you're going to have to do 150.75 grams, because you add 150 and 0.75, and then you multiply this with a million, which can be just 10 to the power of 6, and this gives you about 4,975 ppm. Here's another example. So this one is saying, what are the grams of solute required to make a 3 ppm solution when the amount of solution is 150 grams? So if we once again fill the numbers in the equation, the ppm is given, which is 3. The grams of the solute is x, and then we have 150 grams of the solution, and we're going to multiply this with a million for now. But then let's try to rearrange the equation. So the first thing that we can get rid of is the million. So let's go ahead and divide the million on both sides. So that is going to cancel the million over here. And then the next thing that we can get rid of is the 150 grams. So if we multiply 150 grams on both sides, that's going to cancel it here, and we'll have 150 grams multiplying on the other side. So then the x is just going to be equal to 150 times 3 divided by a million. So that gives you about 0.00045 grams of the solute. which you can also write in scientific notation. So remember, our decimal should be after the first non-zero digit. So that's 4.5 times 10 to the power of, because we are moving the decimal 1, 2, 3, 4, 1, 2, 3, 4 times to the left. So it's going to be negative 4 grams. Alrighty, so let's think about this unit. Let's talk about what we know of as the colligative properties of solutions. So the basic point of these properties is that if you compare a solution to the pure solvent, the melting and boiling point is going to be different. So if you take a solvent and you add a solute to it, its melting and boiling point is going to change. And so in general, the we can say that the thing that is hot gets hotter and what's cold gets colder. So what we mean by that is if you're trying to boil something, that thing is going to boil at an even higher temperature, and if you're trying to freeze something, then the substance is going to freeze at an even lower temperature. And it really depends on the amount of moles of the solute that we are putting in the solution. So let's compare these substances over here. If we put sodium chloride in our solution, when it goes in the solution, it's going to dissociate and produce two ions. If we put potassium chloride in the solution, this one is going to go in the solution and produce two ions again. But if we put calcium chloride in the solution, this one is going to dissociate into three ions. Right? So out of these three, calcium chloride is going to cause the biggest change in the boiling and freezing points. And besides just the number of ions, if we change the concentration, for example, if I put 0.5 moles of sodium chloride, but only 0.1 moles of KCl and CaCl2, then the 0.5 moles is going to have a much greater impact compared to the 0.1 moles. So we define these two properties for freezing and boiling point as boiling point elevation and freezing point depression. So boiling point elevation means that when we are looking at an aqueous solution, it's going to boil at a higher temperature than water itself. So water is the solvent, which boils at 100 degrees Celsius. So if you are making an aqueous solution, then the boiling point of that solution is going to be higher than 100 degrees Celsius. So the reason for that is because when we are adding the salt, it raises the boiling point, and that's because there is a greater concentration of the ions in the solution. So the ions are going to have more intermolecular forces with the water molecules. So it's going to take us a longer period of time to break those intermolecular forces and boil the solution. So remember that the higher the concentration is, the higher the boiling point is going to be. So freezing point is going to be lower because again, it's going to take a longer time to freeze. So normally water freezes at 0 degrees Celsius. If you are looking at salt water or just any aqueous solution, its freezing point is going to be lower than 0 degrees Celsius. So once again, the higher the concentration of our solution, the lower the freezing point is going to be. So as I just mentioned, the way it works is that we have something called the molecule ion attractions when we dissolve a substance in any solvent. So our ionic substances break down into ions, and then they have these attractions with the water molecules or with the solvent molecules. And the thing to remember about these attractions is that they are even stronger than the hydrogen bonding. And these are a type of intermolecular forces, by the way. So they take a very long time to break. So the more time it takes to break them, the more time it takes for us to boil or freeze the substance that we are trying to boil or freeze. So that was the end of solutions. Happy learning.